we're going to look at the conditions for regression inference, which are the most involved group of conditions that we have seen so far and that we will see. There are actually 5 different things we have to check, but I want you to think about specifically the 4 things we have to look at in order to check those 5 conditions. We have to look at the scatter plot of the data. We have to look at the residual plot. We have to think about how the data were collected, and we have to look at a graph of the residuals. Okay, so for both independent and random, we're thinking about how the data was collected. For both equal standard deviation and linear, we're looking at the residual plot. For normal, the graph of the residuals, and for linear, the scatter plot of the data. So you can definitely pause and get this down. I'm not going to read through all of this because all of this comes directly from the book. What we're going to do now, though, is apply these conditions to an example. So we're going to look at the example of the Old Faithful eruptions. So if I go to my next slide here, we're going to look at these 3 graphs. This is the scatter plot of the data. These are the residuals, and this is the histogram of the residuals. So let's look at the different conditions that we need to check. And I'm actually going to pull these graphs out and look at them a little more closely on a separate page. So let's look at the 5 conditions and how we check for them. The first condition is linear. We want to look at, does it look reasonable that the data, that the x and y values have a linear relationship? So here's the sample, a sample of the duration of the eruptions, and here's the interval, or the time till the next eruption. And if I look here, that looks very reasonable that the data looks linear. Okay, we don't see any obvious curve here. So we say the scatter plot looks straight. The scatter plot, I need to say specifically, the scatter plot of the data is fairly linear. Okay, and now we look at the residuals. Here's the line where the residuals equal 0. Okay, so we're saying, is there a fairly random scatter of residuals above and below the line y equals 0 where we don't see any particular pattern? Okay, so there's no obvious pattern in the residual plot. No obvious pattern in the residual plot. We also notice that there seems to, for every x value, for the most part, most of the x, the y's are fairly well scattered on either side of the line where the residual is equal to 0. So this is fine for linear. Okay. For the next one is, we're using the acronym LINER, kind of like linear, only without the A. I means independent. So we think about how the data was collected. This is a random sample of 20 eruptions out of 222 that were recorded in a month's time for the Old Faithful geyser. So we have a random sample of less than 10% of the population. Forgot the word than 10% of the population of eruptions. So the data are independent. In other words, one of them shouldn't have any relationship to the other since I selected them randomly. The third is normal. We want to know specifically if the residuals follow a normal model. Now, let me talk just a little bit about this. If we have a lot of data, and let me try to look at an example of that. This is the entire population of the 222 observations of duration and interval for the Old Faithful geyser. Now, what the normal assumption is that for every x value, so let me just pick one x value here. So let's say here's the duration length. Here are all the y values for that x value. We're saying for every x value the y values cluster around the line of best fit, as if the line of best fit was the actual, or the predicted y value was the center of a normal distribution. In other words, I say for every x value, the y values are distributed fairly normally around the line of best fit, with most of them closer to the line of best fit and a few scattered either side. So we notice that for every x value, it looks like there's a fairly similar amount of y values on either side of the line of best fit, and that they're clustered fairly closely to the line of best fit. So this is an assumption that we are testing. Now, when we look at our sample data, we don't have enough y values for each x value to see that. So we know that when we combine normally distributed random variables, we add them together, their sum is also a normal random variable. So we're just going to throw all of our residuals together, and we're going to see if they follow a normal model or if they have no obvious skew or outliers. So we make a histogram of the residuals. We see that the histogram of the residuals is fairly unimodal and symmetric. So we'll check the histogram of the residuals. If we have a small sample, we might check a normal probability plot to see if it's fairly straight instead of the histogram. But we say that the histogram of the residuals has no obvious skew or extreme outliers. Outliers, not altiers. Outliers. So it is reasonable to assume residuals are approximately, well, I should say, let's just say to assume the normality condition is satisfied. Okay, and the normality is what I just explained, that for every x value that y follows the normal model. Okay, so we have linear independent normal. The third one is E. Okay, so E is, I'll kind of go down a little farther here. E is equal variance or equal standard deviation. Basically, we're saying equal amount of spread in the residual. Equal variance. So we're going to look at, once again, in the residual plot. What we want to notice about the residual plot is that as we move from lower x's to higher x's, the spread of the residuals in the above and below the zero line doesn't really change much. So in other words, we don't have just small amounts of spread here and then really large amounts of spread here. We notice the amount of spread doesn't really change a whole lot. We seem to have a little less spread here in the ends, the middle seems to have a little more, but we don't see any overall trend of getting bigger or getting smaller as we move from smaller to larger x's. An example of a bad variance, so this would violate equal variance, would be if we had the residuals kind of look like this, and then as we move to higher values of x, we notice that the residuals in general, so kind of spreading out here, the residuals are getting bigger kind of as we go from small x to large x. We notice that the residuals are getting bigger, or the opposite, as we go from small x to large x, the residuals are all getting smaller. Here we don't notice a pattern of either increasing or decreasing. So we can say we don't notice any decrease or increase in the variability of the residuals as as we move from smaller to larger x values. Another way of saying that, okay, and I'm going to say maybe any obvious decrease. Kind of have my little example here. My small x is kind of in the way. Any obvious decrease or increase, because we might notice a slight thing here or there. Another thing to say is that we could say that the size of the residuals, you know, above and below the line y equals 0 is about the same all across those values of x. Or there's about equal amount of variability as x goes from small to large. There's a lot of different ways to say that, but basically you understand hopefully the concept and how to describe that. The last one is random, which is our pretty basic one. Once again, think about how the data was collected. We have a random sample of observations. Okay, so that condition is satisfied. Notice that if we have a random sample, that it also satisfies the independent condition. Sometimes we don't have a random sample. We might have random assignment to groups or something like that, and we might have to talk a little bit more about how the independence condition was satisfied. If this seems like a lot of writing and a lot of thinking about conditions, yes, it does. Now, what would I say at the end? I would say there was no obvious violation of conditions. So we're going to proceed with our inference procedure. Proceed, in this case, with a linear regression t-interval. And then, of course, if we're doing a hypothesis or t-test. Okay? Now, notice I'm not completely 100% convinced that all of these conditions are satisfied. I just don't see any reason to think they aren't. Okay, so we're looking for obvious violations. We're looking for obvious curves. We're looking for obvious skew or outliers. We're looking for violations, obvious violations of randomization. If we don't see obvious violations, then we might comment a little, but we're just going to go ahead and check and say, hey, we don't see any obvious problems, so we're going to go on with our inference procedure. So hopefully that's helpful with you in talking about the conditions, recognizing that it is a lot of work to check the conditions for a linear regression situation.